All right, let's look at the Laplace transforms of integrals. All right, so Laplace transform of integral from 0 to t f of tau d tau is equal to Laplace transform of f divided by s, right? Which is equivalently inverse Laplace transform of capital F of s over s is equal to integral from 0 to t f of tau d tau. All right, so let's prove this statement. So here's a proof. All right, so first thing I would do is I'm going to actually call this guy, the integral, g of t. All right, so we're looking for a Laplace transform of g of t. Right, using fundamental theorem of calculus, we know that derivative of f, g, is going to be f, right? So if you want to say, let's see, if you want to find f's of s, which is the Laplace transform of f of t, right? But the f of t is really the same thing as the derivative of g prime of t, derivative of g of t, right? And we know how to take the Laplace transform of derivative, right? So this is going to be s times Laplace transform of the original function g of t minus g of 0, right? But in this case, g of 0, so if you plug in 0 here, it's an integral from 0 to 0. So this guy is actually just 0, right? Then what we are looking for is this guy, right? Laplace transform of g of t. That's the same thing as the left-hand side of the equation we are trying to prove. So all we have to do is divide through by s, then we're there, because capital F of s divided by s is same thing as Laplace transform of g of t, which is integral from 0 to t f of tau d tau. Right? So that's that. All right, let's look at a couple of examples. All right, so let's try to find the inverse Laplace transform of 1 over s times quantity s minus s. All right, so I'm going to identify capital F of s. So you can see that here, leaving a s, this remainder is capital F of s. All right. Then from here, we can figure out the f of t, right? Because inverse Laplace transform of 1 over s minus 3 is the exponential function e to the 3t, right? So all you have to do to find it is just do the integral. So we have an integral from 0 to t. Then we have a e to the 3 tau d tau, right? Then find the antiderivative, which is e to the 3 tau over 3. Then you're going from 0 to t. Right? Then we can just put the 1/3 outside. Right? Plug in t, you get e to the 3t minus plug in 0, e to the 0 is 1. Right? So you can see that we found the inverse Laplace transform by taking the antiderivative. Right? So let's look at another one. This is basically the same trick. Right? So we're going to look at capital F of s, which is, oops, sorry, this is not what I wanted to do. Capital F of s is this guy right here. Right? So this is capital F of s. Right? I'm going to do a little bit of rewriting so that it's easier to find the inverse Laplace transform. So you have s squared on the bottom, and 4, I'm going to write it as a 2 squared. And I would like to have a 2 on top, so I'm going to actually multiply by 2 and divide it by 2. Right? So we can see that f of t is, all right, 1/2 is just a constant to put that there. All right, inverse Laplace transform of 2 over s squared plus 2 squared is a sine of 2t. All right, so all we have to do is integrate that. So integrate from 0 to t. So we have a 1/2 sine of 2 tau d tau. All right, so 1/2 is just a number, put it outside. All right, then antiderivative sine of 2t is negative cosine of 2 tau over 2. Then you're going from 0 to t. So this is going to be, so I'm going to combine 1/2 and 1/2 into, I'm going to get 1/4. All right, plug in t, so you have a negative cosine of 2t minus, so that's going to be plus, I plug in 0, cosine of 0 is 1, so it's plus 1, so I'm going to put that there. All right, so this is the inverse Laplace transform that we're looking for. All right, that's it. I hope that this was clear.